Hi folks, so today I want to talk about sextant navigation. Now I know the guys over at Flat Earth Debate have been speaking about this for quite some time now, and I agree with everything they say on the subject, and in fact I'll touch on a bit of what they say at the end of this video. But I want to focus on a different aspect of sextant navigation today, one that perhaps has never been thought of before, perhaps has, but never modelled, and I'm going to model it. So let's start by begging the question and assuming we're on a sphere, and we want to determine our location on this sphere using a sextant. Now bearing in mind that we must start with a sphere if that's what we're living on, and the geometry must also work on a sphere if that's what we're living on. Now in order to do a triangulation using a sextant, we use the Mercator projection map as shown here. But how do we get a flat Mercator projection map from a globe? I'll let this guy explain.
Projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map.
Okay, so we now know how a projection is made from a globe to a flat map. In this case, the Mercator projection. So we all know that in order to do a sextant triangulation, you need to use a nautical almanac to give you the zenith of the celestial bodies, and you draw circles of equal altitude from that zenith to determine where they cross, and hence where your location is. So for shits and giggles, I'm just going to start by drawing a load of circles all over this map, like so. And then I'm going to take this map and wrap it around a sphere in AutoCAD. And on first glance, everything probably looks normal. These circles look okay, this circle looks okay, but this one, you'll see it starting to go egg-shaped. And if we go down and look at this one, which reaches to the South Pole, this one gets pointed. So the circles are okay around the equator areas, although they won't be a perfect circle. And the further north or south they get, the more egg-shaped or even teardrop-shaped they become. And the reason is because when you try to wrap a projected flat map, specifically the Mercator map in this instance, around a sphere, you have excess map. The paper that the map is printed on will not physically wrap around a sphere. You have to take slices out of the paper on the north and the south to be able to fit the projection back onto the sphere. So it's taken part of the circles out, and in this case made a teardrop shape. Okay, with all that being said, I'm going to simulate a couple of sextant readings to try and determine our location on the sphere. So I'm flipping back to the Mercator map, and I'm going to choose two celestial bodies to take my angle measurements to, that being this one and this one. So GP is the geographical position of that celestial body above the Earth at that particular time. So this one, reading from the nautical almanac, tells me that the radius of the circle I need to draw is 2,000 miles. This one, the almanac tells me I need to draw a 2,500 mile radius circle. And wherever those two circles cross is a possible location that we are on the Earth. So it could either be here or it could be here. If we wanted to determine exactly which one of those it was, we would draw a third, hence triangulation. And the circle would either cross this one or it will cross this one. But we're just going to do two on this occasion. And we're going to say that we know where we are, we know we're not on this one, we know we're on this one because we started out in Greenland, let's say, and now we're halfway between Greenland and Iceland. All fine and dandy, we've located our position. But what happens if we want to put this back onto the globe? After all, it absolutely must work on a globe, if that's what we live on. So here I have again wrapped the Mercator projection with the circles of equal altitude back around the globe. So we're reverse engineering it here. And as expected, we've got some teardrop shapes going on. So I've gone ahead and drawn the celestial objects in AutoCAD. They're obviously not to scale, they're just to give us some angles to work with. So you've got one here right above this GP point, and then one here right above this GP point. Okay, so from the crossing point here, I've drawn a line up to the celestial object, and I've drawn an arc following the surface of the Earth from the GP position to the point where they cross. Now, if you remember earlier, this circle, when we drew it on the Mercator projection, was 2,000 miles in radius. So let's just go and interrogate this arc and see what the arc length is now. And luckily we can do that by clicking. You can see it's highlighted the arc. We scroll down here to the properties, and the arc length is 1,750 miles. So quite significantly shorter than the 2,000 miles that it was drawn on the Mercator projection. So let's go and have a look at the other arc. So selecting the arc, scroll down, arc length 1,415 miles, so even shorter. So almost 600 miles shorter than the circle radius that we drew on the Mercator projection. So I keep saying that if we're living on a globe, then the geometry should also work on a globe. And I think it's a misconception that people have, is that a circle of equal altitude on the globe will actually look like this. However, in reality, the red teardrop shapes shown here are directly interpolated from the flat Mercator projection. And if you look at the locations that these red lines pass through on the Earth, you look at the continents and the land features, you'll see that matches exactly the circles on the Mercator projection map. So there's absolutely no possible way you can triangulate your position on a globe that has been transposed from a flat Mercator map. So this then begs the question, why are we even drawing circles on the Mercator projection? A circle just seems arbitrary, considering it translates to a non-symmetrical shape on a globe with no common radius value. If we are truly living on a globe, then we need to be able to triangulate our position on a globe, and it just doesn't work. The reason we use a flat map, and it works every time, and has done for the last couple of 100 years, is because the Earth is flat. Okay, to briefly touch on what the guys over at Flat Earth Debate have been saying, we're going to use the exact same examples of the GP positions here. I'm going to look at it from an orthographic view. Okay, if we're standing here on the Earth, this is the angle to the celestial body. Let's take a line from our position, representing the horizon. The angle formed here is definitely not 90 degrees. And even at the position where it meets the Earth, you can't have a 90-degree angle to a curved surface. And AutoCAD will actually verify this, because if I choose the angular dimension command and I pick this line and this line, it will give me an angle between them. If I try to pick this line and this arc, it says here object selected is not a line, so it will just not give me an angle. And why would it? How could it? The angle will be different at every single point on that arc. So the question is, to the people who believe we live on a globe, 1. Where are you getting your 90 degrees? 2. Where are you getting your straight line to form the 90 degrees? And 3. Where are you getting your circle of equal altitude? Because from what I'm seeing, none of them are available to us using a sphere. Thanks for watching, folks.